Parallel axis theorem. We want to find out the moment of inertia of an object along an axis which is parallel to the center of mass and separated by a distance L. This is the axis, Z axis, about which we are going to find out the center of mass, to find out the moment of inertia of an object. It is at a separation L from this axis, which is an axis passing through the center of mass, this is the center of mass, and parallel to the Z axis, or the axis which we are considering to find out the moment of inertia. So this is the axis about which we need to find out the moment of inertia I. And this is an axis which is parallel to the axis which we have considered, but passing through the center of mass. So the moment of inertia about an axis passing through the center of mass is I0. And the separation between these two axes is L. So according to parallel axis theorem, the moment of inertia of this object about an axis is I equal to I0 plus ml square, where L is the distance between these two parallel axes. Now let us see how we can derive this. The object we have considered into small particles. One such particle, jth particle of mass small m, we are considering. Total mass of the object is capital M. So one small particle, jth particle we have considered here. It is at a distance rho j from the z axis, which is the axis about which we are finding out the moment of inertia. Now this is the axis through the center of mass and parallel to z. So this is the position vector of center of mass R, that is from the origin, is xi plus yj plus zk. Now we are going to consider R perpendicular to z axis, means it won't have z component because it is parallel to, this axis is parallel to the z axis. So we can write R perpendicular as xi plus yj. It won't have the z component, right? Now, vector from the axis through center of mass to the particle j. This is the axis through center of mass to the particle j. The vector is rho j prime. It is rho j prime or rho j dash. Moment of inertia about center of mass. About the center of mass, if you consider, about the center of mass means the axis passing through the center of mass and parallel to z axis. The moment of inertia I0 will be equal to sum over mj rho j prime square or rho j dash square. That means mj rho j dash square is the moment of inertia of the jth particle. Like that, you will be summing up all the particles which constitute the body. So I0 will be equal to sum over mj rho j prime square. You look at this vector. This is rho j in this direction. This is R perpendicular. This is rho j prime. So I can write R perpendicular plus rho j prime equal to rho j. Rj prime plus rho j prime plus R perpendicular equal to rho j. So the moment of inertia about z axis of the particle j will be mj rho j square. So to find out the total moment of inertia of this object about the z axis, you will be having to take sum over all such particles, that is sum over mj rho j prime square. Now I can substitute for rho j as rho j prime plus R perpendicular. The substitution I have made here. This is of the form a plus b the whole square, which I can expand as a square plus 2ab plus b square. So this is the term you are getting. In this, the middle term vanishes. How the middle term vanishes? Let us see. The middle term consists of sum over mj 2 into rho j prime dot R perpendicular. So the 2 is a constant. Now look at the other part. This is equal to 0. How this becomes equal to 0? This is equal to 0 because sum over mj rho j prime this is a constant. This is equal to sum over mj into rho j prime is rho j minus r perpendicular. That we have shown just now, we have discussed that. So from this expression, rho j prime is rho j minus r perpendicular. So that substitution we have made here, so that you get sum over mj rho j minus sum over mj r perpendicular. Sum over mj rho j is, look at this figure, mj rho j is actually the moment of inertia of this object along r perpendicular. So that becomes m r perpendicular. If it is about center of mass, in the normal case, when we sum over mj rho j, we get m into r. Here we have considered the axis which is parallel to z axis. So the component of r will be r perpendicular. Z component will be 0. So this becomes m r perpendicular. Now look at this. This is sum over mj r perpendicular. That means sum r perpendicular is a constant. So when you sum it up, you get sum over mj, which is the total mass m. So that will be m into r perpendicular. So these terms will cancel, equal to 0. So the middle term vanishes. The remaining part will contain I equal to, these are the remaining terms. This is mj rho j prime square is the moment of inertia about the center of mass, axis passing through the center of mass and parallel to z axis, this one, that is I0, and this is r perpendicular is equal to the length L. The length L is the separation between these two. So you can make the substitution. So this becomes I0 plus ml square. So I equal to I0 plus ml square. This is the parallel axis theorem we have proved. I0 is the moment of inertia about this axis passing through the center of mass and parallel to the axis we have considered. L is the distance between these two axes. M is the total mass. Now we can look at an example. Moment of inertia of a stick about an axis perpendicular and passing through its midpoint is ml square by 12. We have proved in the previous case. Now about an axis at its end, we have to find out about an axis at its end, and the total length is L. If the axis is about the center of mass, the moment of inertia is ml square by 12. We are finding it out. Now the axis is here. The distance of this axis from the center of mass is half the length, that is L by 2. So we'll apply this formula, I equal to I0 plus ml square. I0 is ml square by 12. So IA means along the axis, IA, along this axis. IA is equal to I0 ml square by 12 plus m into the distance between the two axes is L by 2. So L by 2 the whole square. Substituting and rearranging, you get this equal to ml square by 3. The same thing we have obtained in the previous case also. Similarly, we can find out moment of inertia of a disk about an axis at its rim. We know the moment of inertia of the disk about an axis passing through the center. That is mr square by 2. We have derived earlier. So to apply the parallel axis theorem, the moment of inertia about an axis A, it will be moment of inertia about the center of mass, that is mr square by 2 plus m into the distance between these two axes is r, so r square. So add it up, you get 3 by 2 mr square. This is the moment of inertia of a disk about an axis at its rim and perpendicular to the plane of the disk. Like this you can solve various problems. You try out more examples.